Bitcoin transaction in plain English. At high level, Bitcoin transaction moves value by spending old outputs and creating new outputs. Inputs are the previous outputs being spent, and outputs are the new recipients receiving the value. In this example, one input is spent and two new outputs are created. The fee is simply inputs minus output, and the difference goes to the miner who includes this transaction in the block, making this transaction possible. Now, this fee here depends specifically on the virtual bytes or the V bytes, because miners prioritize transaction based on the fee rate per V byte. Now, this transaction weight determines the V byte. SegWit reduces weight by discounting witness data, which lowers the fees. Now, witness data contains signatures. With SegWit, that data is separated and counted differently. Now, that's also why SegWit has both transaction ID and witness transaction ID. The witness data changes the witness transaction ID, but not the transaction ID, preventing the transaction malleability. You can also see the script or addresses type used here. In general, we have P2PKH and P2SH. The P2WPKH are SegWit formats, and P2TR is Taproot, the newest format with improved privacy and flexibility. We usually have OP written codes as well. Now, transaction does not signals RBF, but a transaction which signals RBF means that it can be replaced with a higher fee version before confirmation. That's controlled by the end sequence field. Now, transaction can also use log time or time logs. So, absolute time logs prevent mining before a specific block height or time, and relative time logs delay spending for a certain number of blocks after confirmation. Now, our SegWit transaction discount view shows the actual transaction weight compared to the what it could have been. So you can see the visually see the fee savings here. Now, this is how Chainlinks helps us analyze the transactions.